In 1976, the Viking 1 mission touched down on Mars, carrying experiments designed to detect life. The results were inconclusive, but the hunt didn't stop there. Fast forward to today, and we're using tools like the James Webb Space Telescope to scan the atmospheres of distant exoplanets. The stakes are higher than ever. Could we finally be on the verge of a breakthrough? One of the problems with answering that is that the observable universe contains about 2 trillion galaxies, each with billions of stars. That means there are more planets than grains of sand on all Earth's beaches. With numbers this large, the probability suggests life should exist elsewhere. But after decades of searching, we found nothing conclusive. This contradiction is known as the Fermi Paradox. If life is likely, why haven't we detected any signs of it? In 1961, astronomer Frank Drake created an equation to estimate the number of detectable civilizations. The Drake equation multiplies 7 factors like star formation rates and planets per star. Initially, it suggested thousands of active civilizations might exist in our galaxy alone, but we've refined these estimates over time. Now we know many planets orbit in habitable zones, yet intelligent life appears extremely rare or absent. The Kepler Space Telescope discovered over 2,600 exoplanets from 2009 to 2018. About 20% of Sun-like stars have Earth-sized planets in habitable zones. Based on current data, our Milky Way could contain 6 billion potentially habitable planets, but finding actual proof of life is much harder. Distances between stars are immense. Even the closest exoplanet, Proxima b, is 4 light-years away. Our strongest radio signals have only reached about 0.1% of the galaxy's stars. Most detection methods rely on indirect observations of exoplanets. When a planet passes before its star, we analyze how the starlight changes to learn about its atmosphere. This limits us to planets that align perfectly from Earth's viewpoint. We also can't study surface conditions directly on most worlds. Even promising biosignatures like oxygen might have non-biological sources on some planets. The Great Filter theory proposes some barrier prevents life from advancing to detectable levels. This could mean life rarely forms, or civilizations tend to destroy themselves quickly. Another possibility is we're simply too early. The universe may become more hospitable to life in the distant future. Or perhaps intelligent life actively hides its presence for safety reasons. Despite these challenges, the search continues because the payoff would be transformative. Finding even simple extraterrestrial life would prove life isn't unique to Earth. Microbial life on Mars or Europa could show how common biology is in the universe. With new telescopes and detection methods, we're developing better tools to answer these questions. The next generation of observatories may finally give us the data we need to understand our place in the cosmos. Biosignatures and technology is one of the solutions. Scientists have a way to search for life in distant solar systems. They look for chemical fingerprints called biosignatures. These are specific combinations of gases in a planet's atmosphere that might indicate life exists there. The most important ones include oxygen, methane, and water vapor. When these appear together in certain ratios, it suggests biological processes might be at work. Oxygen is particularly interesting because on Earth, most of it comes from plants and algae. But confirming life isn't this simple. These gases can sometimes form without any living things present. The James Webb Space Telescope changed how we study exoplanet atmospheres. When a planet passes in front of its star, JWST analyzes the starlight that filters through the planet's air. Different gases absorb specific colors of light, creating unique patterns scientists can identify. JWST's infrared vision makes it perfect for spotting water vapor and carbon dioxide. But interpretation is tricky. Methane could come from bacteria or volcanic activity. Oxygen might accumulate from plant life or when ultraviolet light splits water molecules. A promising candidate is K218b, a planet 120 light-years away. Recent observations detected dimethyl sulfide in its atmosphere, a gas that on Earth only comes from marine phytoplankton. The planet also has water vapor and carbon dioxide, but scientists caution this doesn't prove life exists there yet. The signal is weak, and some non-biological processes might create similar chemicals. Professor Niku Madhusudhan from Cambridge explains that even if confirmed, any potential biosignature would spark debates about alternative explanations before concluding it's evidence of life. Three main problems make biosignature detection challenging. First, we need multiple observations to verify findings. One detection isn't enough. Second, some planetary conditions can mimic biosignatures through chemistry alone. Third, our technology still can't study Earth-sized planets well around Sun-like stars. Most discoveries happen around smaller, cooler stars where detection is easier. Future telescopes will improve this, but right now, our data has limits. Current research focuses on finding combinations of gases that balance each other. Oxygen and methane destroy each other unless continuously replenished, something life does well. Finding both together would be strong evidence. Scientists also look for atmospheric changes that follow seasons, like gas levels rising and falling with temperature shifts. The next step is developing tools that can detect surface features, like continents or vegetation. Right now, we're limited to atmospheric chemistry, but eventually we might see direct signs of ecosystems from their seasonal color changes across a planet's surface. While the technology keeps improving, the fundamental question remains: if we found convincing biosignatures, how would we confirm they're truly from life? Some propose looking for artificial pollutants or city lights as more definitive proof. Others suggest sending tiny probes to promising nearby systems. Meanwhile, each new telescope brings us closer to answering whether those atmospheric chemicals are just interesting chemistry or something much more significant. The big question that even I want to know: why finding life matters. If we discovered life beyond Earth, how would humanity react? The answers vary dramatically. Some scientists believe it would unite us, creating a shared human identity against the vast backdrop of the cosmos. Others worry it could trigger widespread fear and social upheaval. Looking at history shows how major scientific discoveries change societies. When Copernicus proved Earth wasn't the center of the universe, it shook religious and cultural foundations across Europe. Finding alien life could create an even bigger paradigm shift. Experts like Prof. Michael Doherty from Imperial College London see potential benefits. The discovery of even simple life will allow us a better understanding about how we might have evolved way back those millions of eons ago when we first evolved, she explains. This perspective suggests finding extraterrestrial life could give us new context about our own origins. Microbial life on Mars or Europa might show biology follows universal patterns, while different biochemistry would reveal new possibilities for existence itself. Religious institutions have begun preparing for this possibility. The Vatican Observatory has stated that simple extraterrestrial life wouldn't contradict most faiths. Complex intelligent life presents harder questions though. Would different species share similar concepts of morality or divinity? Philosophers debate whether discovering alien civilizations would force us to redefine what it means to be human. Some suggest it might reduce human exceptionalism, while others believe it could highlight special aspects of our consciousness. Public reaction would depend on how the discovery happens. A slow build-up of evidence for Martian microbes would play out differently than sudden detection of intelligent signals. NASA and other agencies have protocols for announcing potential discoveries carefully to avoid sensationalism. Studies show most people would respond positively to news of microbial life, but reactions to intelligent life are harder to predict. Some surveys suggest many would see it as threatening, while others view it as exciting. Technologically, finding life would spur new research directions. If we discover life using different biochemistry, it could revolutionize medicine and industry. Even finding familiar life forms would raise questions about whether life spreads between planets on asteroids. The search itself has already pushed improvements in telescopes and lab equipment. Future discoveries might drive development of interstellar probes or new communication methods. While we speculate about reactions, one thing remains certain: the search changes us regardless of results. Each mission to Mars and every exoplanet study forces us to reconsider what life requires. Finding nothing would still tell us Earth might be extraordinarily rare, perhaps the only living world in our galactic neighborhood. Either outcome transforms how we see ourselves in the universe's story. With new telescopes coming online, we're getting closer to answers that could arrive within our lifetimes. The next question is, what tools will give us these answers first? Upcoming missions might settle the debate within decades rather than centuries. Some projects aim to directly image Earth-like planets, while others will analyze atmospheres in unprecedented detail. Each technological leap brings new possibilities for discoveries that could happen sooner than we think. What's next in the search? What does our future look like? The search for life beyond Earth is about to take a major leap forward, with new missions and telescopes coming online. NASA's Habitable Worlds Observatory, planned for the 2030s, will be the first space telescope specifically designed to hunt for Earth-like exoplanets and study their atmospheres in detail. It will use a star shade, a large sunshield flying separately to block out the glare of host stars, revealing the faint light from planets themselves. This technology could finally allow us to directly observe smaller, rocky worlds in habitable zones. Meanwhile, construction is underway on the extremely large telescope, ELT, in Chile. When completed later this decade, its 39-meter mirror, nearly 4 times wider than today's largest telescopes, will collect enough light to analyze exoplanet atmospheres with unprecedented precision. The ELT may detect subtle chemical signatures invisible to current instruments. Together with the James Webb Space Telescope, these instruments represent a new generation of tools pushing the boundaries of what we can observe. But significant challenges remain. Current technology still struggles to detect Earth-sized planets around Sun-like stars, especially when they don't pass directly between the star and our viewpoint. Most exoplanet discoveries so far involve larger planets or those orbiting smaller, dimmer stars. Future missions aim to close this gap. The Habitable Worlds Observatory should be sensitive enough to study dozens of Earth analogues, searching their atmospheres for combinations of oxygen, methane, and water vapor that might indicate life. Several robotic missions will explore our solar system for signs of life. The ESA's ExoMars rover, launching in 2028, will drill up to 2 meters below the Martian surface, deep enough to find biosignatures protected from harsh surface radiation. That same year, China's Tianwen-3 mission will attempt to bring Mars samples back to Earth by 2031. Allowing lab analysis that could reveal microscopic fossils or organic molecules. Titan, Saturn's moon, with liquid methane lakes, will get its own visitor when NASA's Dragonfly arrives in 2034. This drone-like rotorcraft will investigate Titan's complex chemistry across multiple locations. The timeline for potential discoveries is shrinking. Where previous generations could only speculate, we now have telescopes powerful enough to analyze alien atmospheres and spacecraft capable of visiting promising locations. The next 2 decades could answer whether life exists elsewhere in our solar system or whether biosignatures appear on exoplanets. Each new mission builds on the last, gradually eliminating possibilities and narrowing the search. Scientists caution that finding definitive proof may take longer. Misinterpretations are easy when dealing with faint signals across interstellar distances, but the tools now in development give us our best chance yet. This period marks a turning point in the search. For the first time in history, we have both the technology and the strategy to realistically pursue answers to humanity's oldest question. Whether through direct imaging of exoplanets, analysis of returned samples, or robotic exploration of ocean moons, discoveries could happen within many of our lifetimes. The coming years will test our theories about how common life might be while revealing unexpected aspects of planetary systems. Every null result still informs us, and every potential detection pushes us closer to understanding whether Earth's life is unique. The search for life beyond Earth changes us regardless of what we find. Every mission pushes technology forward, from better telescopes to smarter rovers, creating tools that help us understand our own planet too. If we discover life, it would reshape science and philosophy. If we don't, it still teaches us how rare or resilient life might be in the universe. This journey answers more than just whether we're alone. It drives innovation, inspires new generations, and forces us to rethink what life requires. Now we want to hear what you think. Will we find evidence of extraterrestrial life in your lifetime? Drop your thoughts in the comments.